Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, Ricardo Lopes, and today I'm joined by Dr. Donald Hoffman. He is a professor in the Department of Cognitive Sciences at the University of California, Irvine. Dr. Hoffman studies consciousness, visual perception, and evolutionary psychology using mathematical models and psychophysical experiments. His research subjects include facial attractiveness, the recognition of shape, the perception of motion and color, the evolution of perception, and the mind-body problem. He has co-authored two technical books, Observer Mechanics and Automotive, Lighting and Human Vision. He's just about to release a new book in August that will be titled The Case Against Reality, Why Evolution Hid the Truth from Our Eyes, and that's basically the topic that we're going to cover up today. It's really counterintuitive, and I guess that for most people it will be a bit hard to understand, but we're going to talk about what is reality, how our perception works, how it constructs the reality that we perceive and that we perceive in our minds, let's put it that way. So very hard topics to cover up today, but Dr. Hoffman, thank you a lot for taking the time to come on the show.
My pleasure, Ricardo. Thank you for having me.
Okay, great. So we're going to talk about how perception works, but you focus mostly on vision, right?
That's right. My research on technical topics is focused on visual perception, how we see objects and their parts, how we perceive motion, and so forth. So I try to do some specific, hard-nosed technical work as well as looking at the big picture.
Right. And perhaps this has a lot of different topics that we could tackle, but what are the aspects of vision that you like to study the most, and what do they tell us about how our visual perception works?
Well, I've been very interested in studying object perception and how we divide objects into parts for object recognition. And I've studied also our perception of three-dimensional shape as we perceive it from the motions of objects. It turns out just from looking at the two-dimensional motions of objects that are projected onto our retinas, we can infer a three-dimensional structure, and we can write down mathematical equations which actually, to a high degree of accuracy, describe the mapping that we seem to make in perception from the two-dimensional motions on our retinas and the three-dimensional objects that we then see. So that allows us actually to try to build even robotic vision systems that can take video images of the moving world and infer a three-dimensional interpretation of the world from the two-dimensional images in the videos. So that's been very interesting to me. What it does is it forces you to be very, very specific about how perception works. If you're trying to actually build, understand human vision with enough precision to build a computer vision system, computers are extremely dumb, and you have to tell them everything.
Right.
Although with deep learning now, you just tell them how to learn, and they can learn stuff. But in this other mode, when you're actually trying to build a system, you actually have to tell the computer everything about it, so you have to really understand it in great detail. So it's a good way to make sure that you are really understanding the topic yourself.
And so could you tell us perhaps about some of the methodological approaches that you have to learn more about, in this case, how vision works? Do you do work with experimental subjects? Do you use artificial intelligence? How do you approach it exactly?
My work has been heavily mathematical, and then testing the predictions of the mathematical theory with human subjects. We'll bring human subjects into the lab, and the mathematics predicts what they should see when we show them various displays. And so we can then test to see how well the match is between the mathematical predictions and the reports that our subjects give us, or the interactions. We might have them use a joystick to report the depths and shapes that they see. And so that's called psychophysics, which is the scientific study of human conscious experiences, but allows us to do it with some precision. I have done a little bit of work, but mostly collaborative work on brain imaging studies, EEG and fMRI, but that's not been my main focus. It's been primarily studying the actual the visual experiences of human subjects and comparing them to the mathematical models. So that's the normal scientific approach. You get a clean, precise theory that makes precise predictions, and you go test to see if those predictions are borne out or not.
Mm-hmm. And do those mathematical models allow for us to know exactly how people perceive things in their minds, that is the exact visual representations that they have, or do we have to resort to people's reports?
Well, yes, these models are fairly abstract in the sense that they give a computation that any system, computer or human, would have to do to, for example, compute a three-dimensional interpretation of the world from moving two-dimensional video images. The precise neural mechanisms or software mechanisms in a computer that do this is a different level of analysis that would require a different kind and a more detailed kind of experiment. That would probably require a combination of psychophysics and some brain imaging, EEG and so forth. And even then, of course, you no matter how much data you collect, and even if it is all as you predicted, you never know that your theory is correct. All you can do is say, I haven't been able to show that my theory is false so far.
Mm-hmm. Yes, I mean, I guess this is a problem for all of science. We have really to create models of reality, and in this case, perhaps it's even harder because you have to try to create mathematical models of things that happen. I'm not sure if realm is the correct word to use here, but at the mental level, and so it's not really possible for us to have direct access to what people experience in their minds, right?
That's right. We have to go through these experimental procedures where they might be not just giving verbal reports, but sometimes we use verbal reports, but other times they'll be interacting. It could be a virtual reality kind of thing where they're interacting with a three-dimensional object, and we're trying to infer from the way that they interact what it is that they're seeing. I think the remarkable thing is that we think of consciousness as sort of a slippery thing that's hard to get your fingers on and so forth. And what I'm saying is we can build that consciousness actually can be studied mathematically. We can actually predict conscious experiences with mathematical precision. And so consciousness, I mean, I think most people would be very, very stunned to realize that we can do mathematical models of consciousness. And it's not all just airy-fairy and slippery, ghostly stuff. We're building mathematical models and testing them. So, and it's the fact that we can actually understand with mathematical precision how our conscious experiences of shapes and colors and motions and objects are constructed, that we can actually then use that information to build virtual realities that immerse you in brand new worlds. If we didn't have that mathematical understanding of with great precision about how your conscious experiences are constructed, we wouldn't be able to create virtual reality and then immerse you in new conscious worlds.
Mm-hmm. Yes, later in the interview we're going to talk a little bit more in depth about your take on consciousness, because I mean, if we get into conversations about consciousness, I've already had a lot of philosophers of mind on the show and even some cognitive scientists. And it seems to me that the real big problem here is that we can't even operationalize correctly what we mean by consciousness to even study it. Right.
Well, I think that we can talk about conscious experiences.
Mm-hmm.
The kinds of problems of consciousness that I'm interested in are not highfalutin things like self-awareness or, high levels of consciousness, some kind of meta levels of consciousness. I'm thinking about things like everyday experiences, like the taste of coffee, the smell of a rose, the feel of velvet, the sound of a trumpet. Those conscious experiences which are familiar to us in everyday life. The question is to try to understand those experiences and to write down mathematical models of those experiences. In some sense, you could turn the whole thing around. It may be that I know nothing, that everything I believe is false. I mean, and I say that honestly. It's quite possible that we know nothing for sure. But if we know anything for sure, we know that we have conscious experiences. That's if anything is given, it's conscious experiences that are given. And all I'm trying to do is say these experiences that we have every day, it turns out if you look at them very, very closely, you find mathematical patterns. You can predict the kinds of experiences that you will have. And so in that sense, there's no deep mystery there in terms of the subject matter. It's in some sense the most close thing to every one of us every day of our lives.
Mm-hmm. So going back to vision, I mean, we can study different properties of vision like color, shape, motion. Is it the case that the brain constructs each of those properties in isolation, or are they interacting with one another and influencing one another, and it's the interaction between them that builds up the representation that we get in our minds of whatever the stimuli that we are getting?
It appears that our perceptual construction of colors and shapes and motions and so forth has a fairly well-connected kind of architecture in the sense that it's not like one part of the system only does color and nothing else. It may be primarily when we look at area V4 of the cortex, we may find that color is featured there, but we'll also find that other things are being, shapes and so forth are actually interacting with it. And so and when you look at the brain architecture, you'll see that there are what we call feed-forward pathways, where it's sort of stimulus-driven, like from area V1 to area V2 to area V3. It's sort of going from the world into the brain. But then the back projections from V4 back to V3 and so forth are huge, in many cases bigger. So when we look at the neural connectivity of the brain, we definitely see that at one level you can say, well, this area does color, but when you look at it more closely, you realize, well, no, it's actually highly interconnected. But there's a deeper level of answer to your question that we'll probably get into later, and that is that I think that neurons don't exist when they're not perceived, and that the brain doesn't exist. So that strictly speaking, my answer would be that the brain creates none of our experiences and so forth. Nevertheless, I think it's a very, very good symbol for us to look at. So I study neuroscience, and I'm all for studying neuroscience, but I'm for a much more sophisticated interpretation of what we're seeing there. We look at the brain and see neurons, and so we assume that neurons really exist. And I think that that's far too quick. I think we look and see neurons, and those are just symbols that we create. There's something going on, and our humble species just comes up with neurons, and we've mistaken our symbol for the truth. But that's a later discussion.
Right. And it's also the case that these perceptual systems that we have, in this case vision, they also interact with other cognitive systems that we have in our brains, let's say in this case. For example, they also interact with memory, right? So
Yeah, absolutely.
we can't really again study them in isolation. It's not that we have sort of a genetic blueprint that builds our brain and predisposes it to process information from the environment in certain predictable ways, let's put it that way, but and that's how we get perception, but there's a constant interaction with other systems like memory.
I would agree that that's the case. There's lots of interactions. There is an interesting limit, though, to the interactions. So, and this is what we call the cognitive impenetrability of perception. The idea is that there are certain cases where we'll see, say, a visual illusion, like I see a three-dimensional cube on a flat piece of paper, or I see some kind of color illusion. And even though I know that what I'm perceiving is an illusion, I can't help it. So my knowledge that I'm perceiving incorrectly, we say that doesn't penetrate into the perceptual system. It doesn't change my perception. And so it's an interesting, it's not simple here. You're right that there's a lot of connectivity, but there are limits that your high level beliefs can partly influence what you see, but largely your perception goes independently of your high level beliefs, which is quite interesting.
Mm-hmm. So, I mean, when we think about the brain, because many people have this idea of the brain that it is subdivided into several different regions and areas, and they are somewhat isolated from one another, and this area processes language, the other area processes memory, the other one vision and audition and things like that. So what would be the best way to think about how the brain is organized? Would it be to think that perhaps there are certain areas that are organized to process certain types of information, and that's what we can say about them, not really that, okay, this is the area that processes language and that's it, or this is the area that processes vision and
Right.
that's it. It's just that perhaps those types of neurons are specialized for processing a particular type of information, and then they are interconnected, and we have several different neural pathways, and that's how we get each different type of cognitive mechanism that we have. Would
Yeah, I
that
would say
be
that
a good
that's
approach?
Yeah, I think that that's what most of my neuroscience colleagues would say now, that there are these networks, these functional networks, like there's a default mode network, and there's a visual attentional network, and so forth. And these span large portions of the brain and have long range connections among them. And so it's more than just this little area does this little thing and that's the end of the story. It's rather these networks themselves seem to be important functional units, and the activation of one network can actually inhibit the activation of another network. And they're sort of global. I mean, they could span from the front of the brain to the back of the brain in one network. So that seems to be, so it's complicated. But you know, one thing that we have to be aware of in neuroscience is that we're not yet sure even what the right level of analysis of the brain mechanisms is. Is it the spiking rates and the synaptic weights, you know, the synaptic connections? Some people think that microtubule behavior within neurons is really, really critical to what's going on. So there is, I think, I mean, an open question as to what's the right level of analysis of neural activity. Right. So right now it's you know, in some sense spiking rates and action potentials and postsynaptic potentials at dendrites and things like that are being looked at. And you know, of course, I think that's quite important, but it may not be the whole story. And so we may have, even just from a neuroscience perspective, we may have some nice discoveries ahead about new ways of thinking about the brain activity.
Mm-hmm. So I guess that another very important ingredient here is for us to understand where all of this comes from, and it's basically due to processes of natural selection that operated on us through long stretches of time. But I mean, I've been having a lot of evolutionary psychologists on the show, so I'm fairly familiar with evolutionary theory. So it's fairly easy for me to understand where this comes from. But basically, what is the evolutionary rationale for the evolution of our perceptual systems, and why they work as they do, and what they are supposed to represent of the world to us?
Right. So there are a variety of perceptual systems in nature, with a lot of different strategies. So when we think about evolution and its effects on perception, we're going to find a bunch of different solutions. All of the solutions have in common that the point of the perceptions is to keep you alive long enough to reproduce. So it's what evolutionary theorists call finding fitness payoffs, and reporting fitness payoffs. I think it's very helpful to think about evolution and evolution by natural selection as like playing a video game. If you play a video game, you have to hunt like crazy for points and work like crazy to get those points. If you do anything else, you're not going to survive. You're not going to get to the next level. But if you are lucky and work really hard and grab enough points, then you'll get to the next level and you can then try something even harder. Natural selection and evolution is like that. What we're doing in life is playing as hard as we can to grab what they call fitness payoffs. These are, in some sense, fitness points that will help you to stay alive long enough to reproduce. And what happens is if you grab enough fitness payoffs, you don't go to the next level, but your genes, your offspring, go to the next level. And I think that's a very, very good analogy. So the point is that the name of the game in evolution is fitness payoffs. Just like the name of the game in a video game is to get the points that you need to get to the next level. If you do anything else, if you just are looking at the beautiful scenery and lollygagging around, you die in a video game. You won't get to the next level. And it's the same thing about evolution by natural selection. Any perceptual systems that do anything except report or present fitness payoffs and how to get them will be outcompeted by another perceptual system which is focused all of its energies on reporting fitness payoffs and how to get them. So as a result, the selection pressures are to, as we say, tune our perceptions, or have our perceptions report fitness payoffs and how to get them. So it's all about that. Now, most of my colleagues say that the way to do that is to have our perceptual systems report the truth. True facts about an objective physical reality, a space-time reality with three-dimensional objects in it and so forth. That their idea is that those of our ancestors who saw reality more accurately had a competitive advantage compared to those who saw reality less accurately. And so the ones with the more accurate perceptions were more likely to pass on their genes, which coded for the more accurate perceptions. They had a competitive advantage in the things in the famous 4Fs: feeding, fighting, fleeing, and mating. And so because they had an advantage by seeing the truth, they would pass on their genes, which coded for perceptual systems, sensory systems that show the truth. And that seems very reasonable. If you think about it, well, of course, seeing the truth is going to make you more fit. But it turns out that's deeply false. Seeing reality as it is an utterly different thing than seeing fitness payoffs. They're utterly different things. And so the question is, how often, if you're actually tuned, if your perceptual systems are being tuned by evolution to report fitness payoffs, what is the probability that you will also be tuned to true structures of the world? And that's where I've been working with my colleagues, and we've actually been able to prove the probability is zero. So it's if your sensory systems are being tuned by evolution to show you fitness payoffs, which everybody would agree is the case. That anybody who buys biology, evolutionary biology would say, of course, we're being tuned to fitness payoffs. They just think that also means you're being tuned to the truth. And that's the question we ask. Does being tuned to fitness payoffs also mean you're being tuned to truth? What I mean by truth, a world that would exist even if there were no creatures to perceive it. That's what I'll mean by an objective reality. So we think about, the Big Bang started 14 billion years ago, the universe that we now perceive, space-time exists, and it's the pre-existing stage in which the drama of life plays out. There are stars and planets and rocks and so forth that would exist even if there were no living creatures, and they really exist and they have their real properties. And the idea is that our sensory systems have been shaped by natural selection to report truths about these pre-existing objects. Not, of course, exhaustive truth. No evolutionary biologist thinks that we're seeing all of the truth. They would say we only see the adaptive aspects of reality, the parts that we need to see to stay alive. But we're seeing those aspects truly. And what I and my colleagues have discovered is that an organism that sees any aspect of reality as it is never more fit than an organism of equal complexity that sees absolutely nothing of reality and is just tuned to the fitness payoffs. So, in other words, seeing the truth will drive you extinct. And focusing only on fitness payoffs is the only way to survive and reproduce. So, natural selection pressures are uniformly against us seeing any aspect of reality as it is. And that means not simply that, I'm looking at that object over there and I'm getting the shape a little bit wrong, or I'm getting the color a little bit wrong. It's much, much deeper than that. It's rather that the very language of space and time and shapes and colors and motions and so forth is the wrong language to describe objective reality. It's just the wrong language. You could not come up with a true description of reality in that language. That's just so physical objects as we perceive them. Like I see an apple. Most of my colleagues would say, when I see an apple, of course I'm not seeing everything. I'm not seeing all the little atoms and molecules, and there's lots that I'm not seeing. But the three-dimensional shape is true. The color is a true representation, and is telling me certain aspects of the reality that are important for my fitness. And I'm saying that entire framework is utterly false. There is nothing about my perception of the apple, its shape or color, that is reporting truths about the objective structure of a world that would exist even if there were no creatures. Rather, it's this, and this is a new field that my colleagues and I are going to have to go into. We've not actually explored this yet. Objects, as we perceive them, right now my colleagues think that the objects as we perceive them are our best reconstruction of the true properties of objects out there. So we use what we call Bayesian inference. We're trying to infer the true properties of objects based on information at the eyes and so forth. And so we use what we call Bayesian inference and assumptions that are built into the brain and so forth to infer the true shapes and colors and motions. And I'm saying that entire framework is utterly wrong-headed. There's nothing to be saved. That we have to rethink our perception of physical objects entirely in evolutionary terms. The problem is this: we have all these fitness payoffs that we have to deal with to stay alive. Right. Forget reality; that's too complicated. That would overwhelm us. Even the fitness payoffs themselves are so informationally dense that we would be overwhelmed if we saw all the details of the fitness payoffs that are involved. So what we have to do in evolution, what evolution has to do, is to take even the fitness payoff information and compress it down into a really simple format that's going to lose a lot of information about fitness payoffs. So it has to keep the information that's absolutely critical to keeping you alive, and it's going to delete information about fitness payouts that, maybe it'll kill you in 100 years, but it won't kill you now, so we're not going to tell you about that. So in other words, physical objects, as we perceive them, are a solution to a computational problem. And we haven't even studied them that way. The computational problem is to represent fitness payoffs in a data compressed format that allows us to understand the fitness payoffs that are relevant to us right now and how we need to act to grab those fitness payoffs. So we have to rethink object perception all the way down to the fundamental. No one is thinking about it this way at all. Objects are a solution to a computational problem. Finding a data structure that compresses all these fitness payoffs adequately, so that we're not overwhelmed, but gives us enough information about fitness payoffs that we can stay alive and reproduce. And that's going to, when we start to pursue objects that way, it's going to be a revolution in how we think about our perception of objects. So you can see this is a completely different way of thinking about it. We're not recovering the truth about objects. We're not, and I used to write papers in this very same vein that, what we're trying to do is recover the true properties of pre-existing objects. That's way too simplistic. Objects themselves are just data structures that we create as we need them, and then we garbage collect them, we destroy them. So this is a radical claim. An object like an apple only exists in the moment you perceive it. Something exists when you're not looking. So I'm not a solipsist. I'm not saying that there's no objective reality. There is an objective reality independent of me, but it's nothing inside space and time, and it's not physical objects. Space and time and physical objects are data structures that we've been shaped to have by evolution to present fitness payoffs and how to obtain them. End of story. And so I'm saying we need to be completely, if we're going to do evolutionary biology, evolutionary psychology, we have to be completely thoroughgoing. It's about fitness payoffs, end of story. The claim that when we go after fitness payoffs we'll also see truth is just utterly false. And so we have to just rethink perception from a completely evolutionary framework. It's about our perceptions of space and time and physical objects are data structures for fitness payoffs, period. And that's what we have to understand.
Okay, so there's a lot there to unpack.
Right.
So would it be correct to say that two of the main reasons why natural selection tends to lead individuals or species which would have an accurate representation of reality to extinction, because in terms of fitness payoffs, as you say, it is much better for us and for other animals and beings to just focus on the aspects of reality that increase our fitness, that is, that increase our chances of surviving and reproducing, and also because having an accurate representation of reality, whatever it is, would be, we would need too much computational power to do it. Would that be two of the main reasons?
Those are both important reasons. That in some sense, seeing the structure of the objective world as it is irrelevant. That's just not the game. It would be, doing that is like someone hunting pawns in the game of chess. You're just playing the wrong game. And if you're hunting pawns, you're going to lose to the guy who's hunting for your king. And so if you're hunting after, if our senses were out there hunting for a description of objective reality, well, they would just be playing absolutely the wrong game. And you can actually show that in a deep way. I'm working on a paper right now with my colleagues that gets at an even deeper aspect of it. What you said was absolutely true, that in some sense it would be too complicated and take too much time and energy to report the truth of the objective world. And when I went into this study, when I first started studying evolution and perception, maybe 12 years ago, that was your intuition was my intuition, that was going to be what I found, that was going to be the deep story, that it's just takes too much time and energy to compute the truth. And so that's why it's going to be, and that certainly is part of it. That certainly is part of it. But there's a deeper aspect to it that I discovered with my team as we ran evolutionary. There's a field called evolutionary game theory. So as we started to actually do the mathematics of evolution and study this in great detail. And it has to do with the notion of fitness payoffs. These points that you're trying to get in the game of life, right? Mm-hmm. And it turns out that the fitness payoffs, from an evolutionary point of view, do depend on objective reality, whatever objective reality might be. So if there's a world, that world, the state of the world does affect the fitness payoffs that you will get, but they also depend on the animal. So take, for example, just a hypothetical metaphor. Suppose that a T-bone steak is part of objective reality. Although I'm saying that nothing inside space and time is objective reality. But that's where our imaginations are limited to. So I'll have to use what we can use to make the point. And then once you make the point, you can throw away you throw it away and get the deeper one. So suppose that a T-bone steak is part of objective reality. How much fitness benefit would a lion get? Well, if the lion is hungry and looking to eat, that T-bone steak would give it a lot of fitness payoffs. But if that same lion is full and looking to mate, then that T-bone steak offers it no fitness payoffs at all. And if you're a cow, it doesn't matter what your state is or what the action, that T-bone steak is not good for you. It's just not. And so that's the point. Fitness payoffs do depend on objective reality, whatever that might be, but they also depend on the organism, its state, and its action. And so now we can ask, well, okay, so even though a fitness payoff it is a function that depends on the world, we can ask, what is the probability that if there is some structure in the world, suppose that the world has a structure like a metric or an order relationship on it or a topology or something like that. There's a nice clean technical question. What is the probability that a fitness payoff function would actually preserve information about that structure in the world? Because everybody would agree from an evolutionary point of view that natural selection is tuning our senses to the fitness payoffs. So the only question then is about perception and reality is if the fitness payoffs actually preserve information about structures in the world, like orders and groups and rings and fields and so forth, that we could ever see them, because we're being tuned to the fitness payoffs. Only if the payoffs actually happen to also preserve structures in the world could we actually then learn to see those structures in the world. So it's a clean technical question. We can use combinatorial theory. And the combinatorics is actually straightforward. You can ask, if the world has a certain number of states, n states, mm-hmm. and the fitness payoffs have m possible values, mm-hmm. then you can quickly show that the total number of payoff functions is m raised to the n power. Very, very simple, m raised to the n power. Because the first state of the world can go to m possible fitness values times the second state of the world can go to m possible fitness values. So you're going to have m times itself n times, so it's m raised to the n. So that's the total number of fitness payoffs. Now you can ask, how many of those fitness payoffs would preserve a structure in the world? Say the world has a total order where state one is actually like the amount of oxygen, right? Oxygen you can have a little bit of oxygen in the air, a modest amount, or a lot of oxygen, like say the percentage of oxygen. That would be a total order on the amount of oxygen in that example. So you can imagine the states of the world having a total order on them. And so you can ask the question, out of all these m to the n fitness payoffs, how many of them would preserve a total order? Mm-hmm. So that they would actually, those would be the fitness payoff functions that would have information about that structure in the world. Mm-hmm. And you can prove, very, very straightforwardly, I can send you the formula, that the probability, that the ratio is zero. That the number of fitness payoffs that preserve the structure divided by the total number of fitness payoffs, that ratio goes precisely to zero as the number of states in the world and the number of fitness payoff values increases to infinity. So So we have a precise answer. The probability is 0 that a fitness payoff preserves a total order. And in fact, for any structure, it's sort of obvious once you think about it, to actually preserve a structure like a total order, a fitness payoff has to satisfy certain exacting equations. It's hard to satisfy those equations. Most payoff functions simply won't satisfy those equations. So you're right that it would be too complicated and take too much time and energy to compute the truth, but it's even deeper than that. The fitness payoffs that we're tuned to erase information about the truth. They erase the structure of the world, almost surely. And that's the really deeper issue. And one objection would be, well, look, what if fitness payoffs are not exactly preserving the truth, but almost preserving the truth, right? So we could imagine, having a little bit of slop in the fitness payoff so that maybe our perceptions would be sort of close to the truth. In the case of the total order, now I can't actually prove a theorem, but in Mathematica, I can actually empirically play with it. And I found that even if you allow lots of slop, so I'll say a fitness payoff, is close to being a homomorphism, or preserving a structure if it has a certain amount of slop. And it turns out that even if you allow a lot of slop, the number of payoff functions that are that close also goes to 0. In other words, even if you allow slop, the number of functions that would still preserve sloppy structure goes to 0 in the case of total orders, and also in the case of something that we call cyclic groups. And we're looking at various structures. So in other words, not even coarse, sloppy approximations of structure are preserved at all. So fitness payoffs simply do not contain the information that would be required for our perceptual systems to evolve to see structure in the world. And I think that and that's stunning, right? That's truly stunning.
Right.
And I think a really simple example can really help people to see this point. Suppose that, think about the oxygen example. And again, I'm just taking that as a metaphor. I'm saying that space and time and physical objects aren't the objective reality, but that's our brain, our perceptions and our imagination are sort of limited by what evolution has given us. So I have to use a metaphor that we can use. So assume, for sake of argument, that oxygen is real. And we know that if you have too little oxygen, you die. If you have too much oxygen, you'll also die. There's a very narrow range of oxygen concentrations in the air that are compatible with life. So suppose we had an organism that evolution is going to shape, and that organism only has 2 colors that it can see, say red and green. That's all it can see, red and green. Mm-hmm. If evolution were shaping that organism to see the truth, what would be the best that it could do to show you the truth about the amount of oxygen in the world? Well, you could imagine that you might say, well, if there's anywhere from 0 oxygen to a middle amount, I'll see that as red. And everything from a middle amount to a whole lot of oxygen concentration, I'll see that as green. That way, when I see red, I know that there's very little oxygen. And when I see green, I know that there's a lot of oxygen. That would be a perception that's giving me as much information as possible about the truth of the world. In this case, the total order relationship of oxygen. But now, compare that with a different way of using those 2 colors. Suppose instead that I'm interested in fitness payoffs and staying alive. Then I would want to use red, for example, to code for there's not enough oxygen or there's too much oxygen. In other words, I'm going to die. So red means you're going to die. And green means you're not going to die, you're going to live. So that would be, so I'm just using the same 2 colors, I'm using them in a very different way. I'm using the colors to tell me about fitness payoffs. And notice that in doing that, I lose information about truth. If I see red, I don't know if that means that there's a little oxygen or a lot of oxygen. I don't know, because a little oxygen or a lot of oxygen will both make me see red. What really matters is the amount of oxygen will kill me. That's what really matters. And so, and in this example, you can really see, as simply as possible, how truth and fitness are not the same thing, and how seeing the truth will kill you, right? Because you won't know what to do. If you see red and green in the truth sense, you won't know when you're about to die. You will just die. Whereas if you see the red and green using the fitness algorithm, you'll never know how much oxygen there is, but at least you'll be alive. So seeing the truth and seeing what you need to stay alive are two very, very different things. And so that example makes it very, very intuitive. But what we show mathematically is that that's generic. That, my little example there, you might say, well, that's just one little example about red and green. We have theorems that say this is the way it always is, almost surely.
Well, this is really counterintuitive. So it's very hard for people to understand what these sorts of things would entail. But since in the first part of the interview we focused mostly on vision, so these same principles, let's say, would also apply to all types of perception, right? Not only the five senses that people think about the most, but also things like, for example, nociception or the perception of pain, thermoception, mechanoception, even proprioception probably. So all of the things that the organism is prepared to experience when interacting with the world would operate under these same principles.
Right? Absolutely. So this is not just visual perception, it's all of our sensory systems that would be operating in this fashion. I absolutely agree. In fact, in some of the sensory systems like smell and taste, most of my colleagues wouldn't say that we're seeing the truth. They would say, of course, if you take the vanilla molecule, what is the true taste of the vanilla molecule? Well, that even that question seems to be the wrong question to ask, right? What could possibly be meant by the true, accurate taste of vanilla? It seems it's quite obvious that there's just an arbitrary relationship between the structure of the vanilla molecule and the taste that we consciously experience. And so it's just a matter of learning that taste is okay, it's not going to kill you, that it's actually healthy. And I'm saying what's obvious in the case of taste is also true in the case of vision, where most people don't think it's true. Seeing an apple is no different than the taste of vanilla. It's completely arbitrarily related to the objective reality. It's only reported fitness payoffs.
Mm-hmm. So I guess that we have another sort of problem here, because since evolutionary theory also predicts variability among individuals, even individuals of the same species, and because we have stochastic events occurring during the development of the brain, then that would mean, I guess, that we can be sure that that's the case, that different people do not experience the world exactly the same way, either in terms of visual representation or olfactory representation or whatever sort of perception, right?
Absolutely. Evolution's not done with us. Humans are not the epitome of evolution. We're not the final product. We're just another species in progress, and so there are all sorts of mutations that are going on, and it's certainly in the cards. Well, we know, for example, in the case of color perception, that, say for men, roughly 2/3 of men have one version of the red cone photoreceptor gene, and 1/3 have a different version. They differ by single nucleotide difference, which leads to just one amino acid difference in the photoreceptor itself, alanine versus serine. And so you can actually take these men into the lab, find out, are you an alanine guy or a serine guy for this red cone photoreceptor, and then you can test their color perceptions. And they make different color matches in the red, orange, yellow part of the spectrum. In other words, roughly 2/3 of men, we have empirical evidence, even though we call them color normal, are seeing the red, orange, yellow part of the spectrum functionally in a different way, slightly different way than the other 1/3 of men. And the same is true also of women, but women are more interesting because the gene is on the X chromosome, and so they get 2 copies of it. It's a little more complicated with women. But we have that. Also, 4% of humans roughly are synesthetes. They have synesthesia, in which effectively evolution is playing with some radically different kinds of connections between sensory systems, or even different formats within our perceptions. So yeah, evolution's not done, and even your identical twin genetically will be slightly different because the genes don't specify the exact wiring. They only specify an algorithm for the wiring to develop.
Mm-hmm. So, what would be the best way to talk about this model of reality that our brains construct? Let's say, would you call it a simulation of reality or an illusion?
Neither. So, from an evolutionary point of view, there's no reason to simulate reality. That's irrelevant. It's all you need is to know what actions will keep you alive and what actions will kill you, and so it's so the way to think about it, I think, is completely different metaphor. That evolution has shaped us with a user interface. Mm-hmm. And that's very different from a simulation. It's a simulation of reality would, in some sense, be trying to, tell you the parts of reality that you need to know, in some sense, modeling it in your head. And that's the standard view, that we build a model in our heads of the aspects of reality that we need. And I'm saying it's utterly different. So I like to think about the desktop on your computer. Mm-hmm. Suppose you're writing an email or writing a book. So yeah, that makes it, the stakes are, you're writing a book, and the icon for your book is blue and rectangular and in the middle of your desktop screen. Does that mean that the book itself in your computer is blue and rectangular and in the middle of your computer? Of course not. Anybody who thought that is just missing the point of the desktop interface. It's not there to show you the truth, which in this metaphor would be the circuits and software and voltages and so forth. I mean, your desktop interface is there to hide that truth. It's there to hide that messy reality. If you had to toggle voltages to write a book, you'd never get published. It would never happen. And so the point of a desktop interface is not to show you the truth. It's explicitly to hide the truth and to give you simple symbols that allow you to control the reality, in this metaphor, control the circuits and software, even though you might not even know that the circuits and software exist. And that's what evolution did for us. Evolution didn't give us a simulation of reality. It gave us an interface to hide reality completely. Reality is hidden utterly and completely from us, from an evolutionary point of view. And space, as we perceive it, is literally just your desktop, a three-dimensional desktop, but a desktop. And physical objects are just three-dimensional icons. They're more functional than two-dimensional. With a three-dimensional icon, you have lots more functionality that you can get, but they're just icons. We'll pretty soon have holographic desktops on our laptops and so forth. So we'll be having a much more functional interfaces, and this idea will actually become quite commonplace. And with the next generation spending a lot of time in really good virtual realities that are quite immersive and quite compelling, this idea will be, I think, to the next generation just sort of obvious. Like, why was this an even big deal at all? When you take off, when you're immersed in virtual reality and is completely compelling, and you have this sense of reality in there, and you take your headset off, it's just going to be an obvious question. You won't have to have a high IQ to say, well, what about the reality with my headset off? Isn't this just another virtual reality? And I'm saying, according to evolution by natural selection, absolutely. That theory predicts that this is just a virtual reality. We've always had a headset on. We've mistaken our little interface, our little virtual reality that was shaped by natural selection only to keep us alive. We've mistaken it as an insight into the truth. So think about space as just your VR three-dimensional space, and physical objects is just VR icons. And just like when you know, if you're playing, say you're playing tennis in virtual reality with a friend, and I pick up a tennis ball in virtual reality and I hit it, we can talk about the tennis ball that I'm hitting and you're hitting back. Of course, and we can both agree that there's a tennis ball. You know, it's green and it says Wilson on it or whatever, and so forth. We can agree, but of course there's no tennis ball there. We're just dealing with circuits and software, and the tennis ball is just a very dumbed down symbol that we can use to control all that, the circuits and software. But, and of course, when I look in a certain direction, my headset gives me pixels that prompt me to create a perception of a tennis ball. But as soon as I turn my headset the other direction, those pixels are no longer there. I destroy that tennis ball. You know, I mean, literally, the tennis ball, the three-dimensional tennis ball with all the nice green color and fuzz on it and so forth that I created, that's gone, because it only existed in my perceptions. It only existed as a data structure that I created and experienced in my perceptions. So obviously in that case, the tennis ball exists when I create it, and I can look away and I destroy it. And I'm claiming that's true in everyday life. To put it very, very bluntly, the sun only exists when I look at it. You have a sun that you create, I have a sun that I create. The moon only exists when I look at it. There is an objective reality, but it's utterly not unlike anything inside space and time. And it's just like, again, there is an objective reality in the virtual reality game, in that metaphor, but it's utterly unlike the tennis ball. It's circuits and software and voltages in that metaphor. And so I'm claiming I create the moon when I look at it, and I destroy the moon when I look away. When I look inside a head, I create neurons. That's my symbol. I create cortex. I create the brain. When I look away, I destroy it. So strictly speaking, right now, I don't have a brain, and I don't have any neurons, because no one is looking and creating brains and neurons. There is some kind of reality, and if someone looked inside my head, they would then see that reality in the language of brains and neurons. But that doesn't mean that that's what exists prior. And so this is a really, really important point. When we say that neural activity causes our behavior, we're wrong. Neurons don't even exist when they're not perceived. Something is there, and when we look at that something, we see it in terms of neurons. But that's just because we're a poor, humble species with a very limited set of symbols, a very limited interface, and that's the way we see it. But worse, we're a species that doesn't even realize that this is just an interface. And we mistake the limits of our interface and the format of our interface as an insight into reality. That's just utterly wrong. So, but it's very, very hard for us to I mean, if you look at human history, we thought the earth was flat. And any bright person could just look around. You didn't have to be that bright and see that it was flat. We mistook a limit of our perception as an insight into reality. It was the fact that we couldn't get away from the earth and see, for example, that it's not flat. I mean, that was a very limit. So eventually some really bright people like Pythagoras figured it out around 500 BC. But then for the next 2,000 years, very, very bright people thought, well, yeah, the earth isn't flat, it's more like a sphere, but it's the center of the universe, and it doesn't move. And you don't have to be too bright to look around. This isn't moving. The earth isn't moving. You just look, it's not moving. And you can see the sun, moon, and stars all go. So clearly we're the center of the universe. And so again, we mistook a limit of our perceptual representation as an insight into reality. And it was really hard for us to let go of that, to realize, no, the way we see is just the way we see. It's not the truth. We actually burned people at the stake, right? The church burned people at the stake who said, no, the earth, is not the center of the universe. Galileo said the earth moves, and the church says, no, it doesn't. But those were just warm-ups. Now we have to let go of space and time and physical objects themselves. We assume that because we perceive a world in terms of three-dimensional space and dimensional time, and we perceive objects like apples and chairs and tables and the sun and moon, that therefore that is the way the universe really is. And I'm saying that's utterly false. And it's the same mistake as flat Earth. We're mistaking a limit or a format of our perceptions as an insight into objective reality. So, for everyday neuroscience, I think it's perfectly fine to talk about neurons and neural activity as though it really exists and has causal powers. And I do that. When I'm doing, my everyday neuroscience, I talk that way because it's just a quick and easy shorthand. I mean, it's sort of cumbersome to talk about, well, it's just an interface, I don't know what the reality is, and so, given that we don't know what the reality is, it's useful to just talk that way. The problem comes when, most of the time, talking about neurons and physical objects as having causal powers is perfectly fine, and it causes us no problems because it's a useful fiction within our interface. Like if I hit a cue ball and it hits the 8-ball in a game of, then we think that the cue ball hitting the 8-ball it has genuine causal powers and causes the 8-ball to move off into the corner pocket or something like that. But strictly speaking, that's false. No physical object in space and time, strictly speaking, has any causal powers, partly because it doesn't even exist when it's not perceived. It's literally just the icon that I create when I need it. So in neuroscience, the problem, for everyday neuroscience, it's perfectly fine to use the fiction of causality. Neural activity causes other neural activity and causes behavior. Perfectly fine, and I do it myself. But when we try to understand the hard problem of consciousness, how is brain activity related to our conscious experiences, like the taste of chocolate? That's when the fiction is no longer harmless. It actually has prevented us from solving that hard problem of consciousness. It's very much like, suppose you're playing a video game, like Grand Theft Auto, and you have a steering wheel there, and you can see the steering wheel. Of course, when you look away, you destroy the steering wheel. But you can assume, for sake of argument, in the game, the steering wheel is real and it really has causal powers. When I turn the steering wheel to the left, it causes the car to go to the left. When I turn the steering wheel to the right, it causes the car to go to the right. For the game, that's perfectly fine. It's a fiction. The steering wheel doesn't even exist. It's only your perception. It really has no causal powers, but as far as the game is concerned, if you believe the steering wheel has causal powers and it really causes the car to turn, that's not a problem. You're going to be fine. It is a problem if you're a software developer and you want to build the game or you want to change the game. If you believe that steering wheel is real and it really has causal powers, good luck. You're never going to really understand what you need to understand to really get the circuits and software coordinated with the perception of the steering wheel. And that's the point here. For everyday neuroscience, we're just inside the game. And that's perfectly fine to have the fiction that area V1 causes activity in area V2, or that activation of the attentional network inhibits the default mode network and things like that. It's perfectly fine to talk that way. It's only when we're trying to get under the hood and ask what's the relationship between conscious experiences and neural activity that now that fiction absolutely destroys any chance of understanding what's going on. And so that's why we've been able to get away with this belief that neurons exist and physical objects exist and have causal powers. Most of science, almost all of science until now, has been a science of our interface. We're still in space and time. Any science that's about what's happening in space and time is just about our interface. We haven't, that science has not yet stepped out to try to model reality. We're now getting to the point where we will have to do that, and so we're going to have to let go of the idea that space-time is fundamental and physical objects have causal powers.
So, what is objective reality then? Because I don't get too much into things related to quantum mechanics and things like that. It's really hard to deal with those sorts of things. But as far as I understand it, even at subatomical level, and when we're dealing with subatomical particles, the state we find them in also is dependent on the observer, right? So I mean, even if there are no physical objects out there, I mean, we're not only referring to physical objects as a table or a chair or an apple. We're also referring to physical objects even at the level of atoms and subatomic particles, right?
That's right.
Those things, as we see them, either represented in any sort of way that the technology that we develop to study them represent them to us. Those same things that we see there on the screen, they also don't exist.
Right. Anything inside space and time is just part of our interface, is part of the way we see, is not part of objective reality.
Mm-hmm.
So that's a pretty broad statement that I'm making there. If what you're studying is in space-time, then it's in our interface, and it's not part of the objective reality. It's that simple and that stunning. And physicists are now beginning to realize this. There's Nima Arkani Hamed, David Gross, Ed Witten, and others have said space-time is doomed. And that's the phrase they use. Space-time is doomed. And if you Google that phrase, if you Google the phrase space-time is doomed, you'll find videos by Nima Arkani Hamed in which he explains why space-time is doomed. Physics for the last few centuries has been about what happens in space-time.
Right.
And now they're saying space-time's had a great run. It was a really good framework for physics, and it's over. There's something deeper. There's a deeper reality, and space-time is not fundamental. It's going to be emergent, only a crude approximation to something far, far deeper, a different kind of reality, and they have no idea what that deeper reality is. But properties like position, momentum, and spin, which are properties inside of objects inside space-time, are not fundamental. And one clear empirical prediction is that properties like position, momentum, and spin, these dynamical physical properties, do not exist, do not take definite values.
It's all probabilistic, right?
That's right. All we can do is write down probabilities about what we will experience, but the idea that they really, that even though we don't know what the value is, that there is a real value, that the electron, we might not be able to know what the exact position is. We have to write down a probabilistic wave function for the position, but of course it really has a position. Well, we know that the technical term for this is non-contextual realism. Some work done by physicists named Kochen and Specker and Bell address the question, do physical objects like electrons have definite values of properties like position, momentum, and spin when they're not observed, and those values do not depend on how we observe them? So it's called non-contextual realism. The realism is the claim that they have definite values when they're not observed, and the non-contextual part is saying the values that they have don't depend on the way we're going to try to observe them or measure them. And it turns out non-contextual realism is just flat out false. They've done the experiments, it's false. Mm-hmm. So that's exactly what I would predict if space-time is just our user interface, and we're like the virtual reality, right? When I look over there, I see that green tennis ball. I'm creating the tennis ball. When I look away, there is no tennis ball to even have a position or momentum because it doesn't exist except in my perception. So it's no surprise that there's no definite value for the position and momentum of that tennis ball when it's not observed, because it only exists when I observe it. And that's the point. What physics is really, I think, saying to us is everything inside space and time just is our interface. It only has properties when they're observed. And there is an objective reality, but it's deeper than space-time. And space-time is just the interface that our species happens to use to represent that. Nima Arkani Hamed actually has some interesting work studying scattering amplitudes at the Large Hadron Collider. Like two gluons, which are these really real tiny particles that are inside, protons even. They're really, really tiny. Two gluons come in and smash, and say four gluons go spraying out. You compute the probabilities of that happening, and those are called scattering amplitudes. And it turns out, when they study them, if you force yourself to stay inside space-time, when you do the computations, you get a mess. You get hundreds of pages of algebra that you have to compute, and it's really hard to do. But when you go to a deeper reality and they don't know what it is, they can just write it down mathematically, but they don't know what this reality is pointing to. All of that mess, hundreds of pages of math, reduces to just one or two terms that you can compute by hand, and they see new symmetries that cannot be captured in space-time. So you have two things lining up that are pointing to us saying, let go of space-time. There are symmetries that are deeper than space-time that are really in the data and are needed to understand the data, but they can't be expressed inside space-time. So that's one strike against space-time. And the second strike is that if you force yourself to do stuff in space-time, you get a mess, which is really just hiding all this deep symmetry. And you're getting hundreds of pages of math that you have to compute. When you do this deeper level reality, that all disappears, and you see that something really simple is going on in this deeper reality. So physics is at this tantalizing point, and the best physicists are not upset about this. They're delighted. So what if space-time has been our framework for centuries, since Newton? So what if we've been wrong for centuries? This is exciting because we're about to, make the exploration into a deeper level of reality and show how space-time and all the theories that we get inside space-time, so general relativity, quantum field theory, evolution by natural selection, these are all theories that only hold inside space-time. They put real deep constraints, though, on whatever deeper theory we're going to come up with, because that deeper theory, when we show how space-time emerges from it, we better get general relativity, quantum field theory, and evolution by natural selection as what we would see in our interface from this deeper reality, whatever it might be. So for me, this is all quite exciting. Evolution and physics are telling us the same story. Evolution is telling us this is just an interface. It's not the truth. And now the physicists are saying, yeah, space-time isn't the truth. There's some deeper reality, and space-time has had a good run, but it's not fundamental. And so I think it's great when evolution and physics are telling us the same thing. Let go of space-time and let go of all the objects inside space-time. They are just an interface, and there's no true causality for anything inside space and time. It's only a fiction of causality.
So, just one last topic. If we are in the future to develop virtual realities or some sort of simulation where we would be feeding our brains with information or stimuli that would stimulate the brain in ways that would produce the same sort of mental experiences that we get when we receive information from the world itself, whatever it is, then what we would get there, if it worked exactly the same way, wouldn't be in any way different from what we already experience, right?
Well, I could imagine that we could stimulate our brains in ways that we have qualitatively different kinds of experiences than what we have now. I mean, some people tell us that when they take drugs, that's what happens, right? That they have these hallucinogenic experiences that are utterly unlike, in some cases, feel even more real than everyday life. So we seem to have firsthand evidence that there are ways to play with our brains that lead to new kinds of experiences. So I don't doubt that we can do more in that direction, and it could be quite powerful. Absolutely.
Mm-hmm. But in any ways, since we're talking about we having an interface of reality, if we could in some way reproduce that same sort of interface in a virtual world, then supposedly people wouldn't be able to distinguish it from the interface that they have from this world. Right.
I could imagine an interface being so compelling that it would be very, very hard for someone to distinguish it. That would be a technology we don't quite have yet, because you also have to have the whole tactile aspect. I think that we'll get there visually very, very quickly. But getting there with all the other senses, that's going to take a little bit of effort. But I don't see any principled reason why not. This is all, right now, this is a virtual reality anyway that we're creating. And there is an interesting question: what is the nature of the ultimate reality? Right. That
right.
If it's not space-time, what is it? And I've been playing with the idea that trying to solve the hard problem of consciousness. I've been playing with the idea that I can build a mathematical model of consciousness that I call conscious agents, and that the universe, the ultimate reality, is a vast social network of interacting conscious agents that can have conscious experiences and that can then affect the conscious experiences of other agents by their choices. And so it's, again, I'm probably wrong, but at least I'm trying to be precise. So I'm trying to solve the hard problem of consciousness. I'm saying, okay, let me start with consciousness and try to show how space, time, and matter could come out, instead of starting with space, time, and matter and trying to boot up consciousness, which is what most of my colleagues are trying to do. And so the idea would be like, think of the universe as like the Twitterverse, right? It's a huge social network. There are millions of Twitter users out there and billions of tweets and lots of things trending. If anybody in Twitter was really trying to understand that, it would be overwhelming. There's, too many tweets to even understand. So how can you deal with it? Well, in the age of big data, we can use visualization tools. We have these nice graphical visualization tools, so I can see what's trending in Los Angeles and what's going on in New York and so forth, and I can compress all that social interaction, all that that Twitterverse, into a three-dimensional space with objects in it that allows me, and colors that lets me understand what's happening. Of course, Twitter doesn't have color, and it's just a graphical tool, and that's what I'm claiming is going on. The ultimate reality is this vast social network of interacting conscious agents that I can talk about mathematically. And what we call space and time and physical objects is just a graphical tool that certain agents, that Homo sapiens, namely, certain agents use to understand this big social network that we're involved in. So we've mistaken our graphical tool for the reality.
But doesn't that mean then that the vision of what reality is that you're trying to develop there, that it would be a subjective reality because it depends on the conscious systems operating on subjects?
That's right. It would be a vast network of subjective experiencers. What I call conscious agents are subjective experiencers. It would be real in the sense that it would exist even if I weren't aware of it. So it doesn't depend on, so again, it's not solipsism, right? Solipsism is the claim that all that exists is me and my experiences. And so this is a rejection of solipsism. It's saying, no, there are other experiences and experiencers out there. And so it is reasonable to have life insurance, right? Life insurance is a good bet on this theory, because the idea is that even if my experience wasn't around, my family's experiences might still be around, and so forth, and much, much further. So it's a kind of realism. I call it conscious realism. It's not a solipsism, and it's not an anti-realism of any kind. It's saying what really exists are the subjective experiences of this infinite social network of conscious agents. And it has the math indicates it has an interesting property that when two agents interact, they also become a new agent. There's a new agent as well. So that the whole network of conscious agents is also one agent. So it's really interesting mathematical structure that we're beginning to study, that there's this one agent, but we can anatomize it into an infinite network of conscious agents and look at its dynamics and so forth. So there's going to be a lot of fun mathematical work that my colleagues and I are doing on.
But would that mean then that there is no reality if we don't have conscious agents?
That's right. That's what this proposal is. I and my colleagues are proposing that the ultimate nature of reality is consciousness. And when I do that, it brings up an important point about science as an endeavor. No scientific theory has ever explained or even tried to explain everything. Every scientific theory always says, grant me these assumptions. These assumptions are not something that can be explained within my theory. But if you grant me those assumptions, then I can explain all this other stuff. So grant me, say, space and time and quantum fields. Then I can explain chemistry and biology and hopefully eventually consciousness. But what about space? Well, at least within that framework, space is a given. It's a miracle. You might try to come now what Nima and these, and David Gross and these guys are doing when they say space-time is doomed. They're saying, okay, we don't want space to be a miracle anymore. We're looking for something deeper. There'll be a deeper notion of reality, but that will be the miracle. That will be the new miracle because that won't be explained. It will be assumed. And every scientific theory always has to assume something, and then it explains everything else. And that's a bit of a bother that we can't explain everything. It's really an interesting situation that we're in as human beings. We can't explain everything. There's always going to be assumptions. I'll call them miracles just to make it really in our face. Assumptions that the theory itself can't explain. And so what I'm doing is I'm proposing that the fundamental unexplained in my scientific theory is the existence of experiences like the taste of chocolate, the smell of garlic, and the ability for those experiences to influence other experiences and other experiencers. Those will be my miracles. What then I have to do is to show how, with that, I can build up what we call space-time and physical objects as just a user interface to that whole social network. And I have to be able to show that I could, for certain kinds of dynamics on that network of conscious agents, I could get back evolution by natural selection as my interface description of that network of dynamics. And I can get back general relativity and quantum field theory, the standard model of physics, as descriptions within my interface of this network of conscious agents, which is utterly outside of space and time.
So you're ultimately looking for a theory of everything. Could we call it that?
Yes, I'm looking for, of course, we have to admit right up front that the chance that we're right is very, very small. But the point is to be, in science, the point is to be precise so that you can find out as quickly as possible precisely where you're wrong. And that's how we make progress. So the goal is to be bold and precise. And that way we can really try, and even if we get the truth, we can't know that we've gotten it, right? We can never prove in science that our theories are correct. All we can try to do is get evidence that, disconfirms, that sort of reduces the credibility of our theories. And then we can say, well, why is the evidence not the way we expected it to be? How do we need to revise our theory so that we can account for that? So, but even if we find that we can't get any evidence that disconfirms our theory, we can never know for sure that we just weren't clever enough to find the right evidence. And that's the human condition. And, I may not be comfortable with it, but that's just the way it is. And so you just have to, just go with it. So that's the game that we have to play. Be precise. What we can do is be precise so that we can find out as quickly as possible precisely why we're wrong. So we'll see.
Okay, great. So, Dr. Hoffman, before we go, apart from your book, that I will leave a link to it in the description box of the video, would you like to make reference to other online sources where people can get in touch with your work?
Yes, I have a web page, and it's easy to get to if you Google Donald Hoffman, Hoffman, my homepage comes up probably one of the first 2 or 3 things that comes up. So it's very easy to get to my homepage. I have links to all of my videos and podcasts and books and papers, and many with free online resources. So if you go to my homepage, there's a link called Vita. And in my Vita, I list everything I've done, and I put as many links to free online sources as possible for the podcast, videos, and books and papers and so forth. So.
Mm-hmm. Okay, so Dr. Hoffman, it was really a pleasure to have you on the show. I'm really looking forward to your book because, I mean, this is a very fascinating topic, and I hope really that it sells well. All the best to you, and again, thank you a lot for taking the time to come on the show.
Thank you, Ricardo. It was a great pleasure to talk with you, and great questions.
Hi there, thank you for coming to my channel and for watching this interview until the end. As you might have noticed, I've been putting out regular interviews with academics and intellectuals from a variety of fields. So to keep the channel sustainable, I would like to ask you to please visit my Patreon page and to consider making a pledge there. Otherwise, I also have a PayPal and Subscribestar. And if you like what I'm doing, please share it, leave a like, and hit the subscription button. I would also like to give a huge thank you to my patrons, Karen Litzke, Anne Blanchett, Perelga Larsen, Lau Guerrero, Chantel Gelinas, Francis Ford, Hans Frederick Sunda, Brian Rivera, Lucas Stafiniak, Sergio Condreano, Iane Henninen, Ricardo Vladimiro, and Dr. Jerry Muller, Herbert Gintis, and Rutger Voss, and also my 3 producers, Isar Webbe, Rosie, and Jim Frank. Thank you for all.